Hi, today I'm going to talk about concentration inequalities for heavy-tailed random variables. So let us start with a motivation. In inverse problems, we are interested in recovering a signal of interest x from its measurements y1 to yn, in which some randomness is involved and the randomness is encoded in AI. So a usual scheme to estimate x is to define an objective cost function and to minimize this cost function to provide an estimation. We can use the usual gradient descent to solve this optimization problem, but note that there is randomness in f and hence in gradient of f. Asymptotically, the gradient of f is behaving similar to its expectation, and hence the deviation of gradient from its expectation is an important quantity. Because of the additive form of f, the gradient has additive form, so it can be seen as sum of random variables. If we assume ai's are IID, zi's would be IID as well. And we are interested in the deviation probability to state the convergence statement with high probability. This probability is directly related to determining the convergence rate of this algorithm and the sample complexity. Formally, we have IID, real valued random variables. We are interested in the upper bound for the deviation probability. And by law of large number, one can easily see if we fix epsilon send n to infinity, this upper bound goes to 0. The question is, what is the rate at which this convergence happens? Epsilon can be fixed or can be a function of n depending on the problem setup. Obtaining a concentration inequality is easy, but not all of concentration inequalities are interesting. We are interested in sharp ones. Here is how we measure the sharpness of the inequality. We take a lower bound and then compare the ratio of lower bound and upper bound. Since we are usually interested in asymptotic setting, we say the inequalities are sharp asymptotically if this ratio goes to 1 as n goes to infinity. You might notice that I motivated the problem for the vectors, but set it up for scalars. One can easily see the scalar's result can be extended to the higher dimension by a projection and by epsilon net argument. It turns out the tail of random variables involved in the summation plays a key role. And in fact, for two important tails, the concentration has been studied extensively. The first class is SubGaussian class, for which the log of tail is a quadratic function. Normal distribution, Bernoulli distribution, and all bounded distribution are members of this class, for which there is a general Hoftin inequality, which basically says we can take the upper bound as the following. So it's an exponential function depending quadratically in epsilon and linearly in n. If we want to send this upper bound to 0, we have to take epsilon greater than 1 over square root n. For another class of exponential, for which the log of tail is linear and chi-squared and exponential distribution are member of this class, we have Bernstein inequality similarly, which says the upper bound can be determined by the maximum of two terms in this form. The first term corresponds to a subgaussian convergence, and it's corresponding to a small epsilons. The other is an exponential deviation. And it's interesting why we have two separate regions. Because of central limit theorem, for small epsilons, we know the behavior of the sum would be similar to Gaussian. And the other region appears when epsilon is larger than a specific value. It's helpful to take a look at the proof techniques of these inequalities. So since a shift does not make anything wrong in our setup, from now on, we assume our random variables are centered. The moment generating function is a key idea in the proof of these inequalities. In fact, a simple Markov inequality says the deviation can be bounded by the following. And since this inequality holds for any positive lambda, one can obtain these inequalities just by optimizing lambda. The story for heavier tails is a bit different, and we're going to see why. So let me define the rate function to be negative log of the tail. Hence, the quadratic rate corresponds to subGaussian class. For the subexponential class, we have linear rate function. And whenever the rate function is sublinear, we are in the case of heavy tail distributions. One might ask how is possible to get heavy tail distribution simply by multiplication. For example, a Gaussian random variable 2 power p, where p is greater than 2, lies on the class of heavy tail distribution. As we saw, MGF is a key function in the proof of the concentration inequalities. And here is the point. When rate function is quadratic, MGF exists on the whole line. When it's linear, it exists on a compact interval containing the origin. And as soon as the rate function gets sublinear, the MGF does not exist anywhere. Hence, the classical proof does not extend to heavy tail distribution. Of course, there have been other works to provide concentration inequality for heavy tails. I've listed some of important ones in the literature here. I would like to move on our contribution in this literature. So recall rate function has this form. I'm going to say function I captures the right tail of random variable z if this inequality holds, if e to the minus it upper bounds the probability for any positive t. And here is the simplified version of our main contribution. So similar to the sub-exponential case, we see two regions. In the first region, for large epsilons, the tail capturing function characterizes the upper bound. For the other region, which corresponds to small epsilon, we see a Gaussian behavior of the deviation. In this inequality, C and beta both are coefficients depending on epsilon, n, and z. But as n goes to infinity, both beta and c are going to 1. So simply you can think of c beta as 1. There's another important coefficient in this inequality, which is in red. I'm going to talk about it more in the next slide. It turns out our concentration inequality is applicable whenever one can bound these important coefficients CL and beta, which is defined in the following. So CL and beta is this expectation in which ZL denotes the truncated version of our random variable Z, L denotes the truncation level, and beta is some coefficient between 0 and 1. For our proof, we're going to set L to be n epsilon, and we're going to send it to infinity for asymptotic studies. If you ignore this exponential term, this expectation is nothing but expectation of ZL squared, which tends to the variance. And hence, whenever the variance of random variable is finite, our inequality are applicable, and basically CL and beta asymptotically goes to the variance of Z. There are more technical details about other constants, but I would like to move on for now. As I mentioned, it's important to show the sharpness of the result. To do so, we're going to fix epsilon, send n to infinity, and actually assess the sharpness of our inequalities. So in the first region, recall that this is the inequality that is given by our result. So u z of n and epsilon can be written in this form. We have shown for two classes of rate function. One corresponds to the subwave random variables, where it is alpha root t, and when the rate function is logarithmic with coefficient greater than 2, that our results are sharp in the same sense that I defined. So this limit is 1. In the second region also, if we rescale the variable epsilon by epsilon prime divided by square root n, we're going to see the familiar form 1 over square root n sum of zi, which converges to a Gaussian distribution. And one can see the dominant term in this inequality is the first term, which is exactly the same bound for the limiting Gaussian distribution. Hence, in this region, the inequality is sharp as well. While I described this sharpness for fixed epsilon, we can actually consider dependence of epsilon to the n, and this has been discussed in our paper in details. Let me sketch the proof quickly. So we have seen that MGF is not existing, and that's the main issue. So here is the idea. We truncate the random variables, and we upper bound the deviation probability by the probability of deviation of truncated random variables plus an error term due to the truncation. Basically, we choose appropriate values for lambda and L, and that is going to give us the inequality we hope for. Because we have to make these two error terms balance, one can see L should be set as n epsilon. And since the ZIL are bounded and hence subgaussian random variable, one might think a simple Hofting inequality can solve the problem from this point. But it's not the case, unfortunately, because the subgaussian norm of this random variable is going to infinity as L is going to infinity. So a naive Hofting bound will blow up the final inequality we are interested in. Also, since the moment generating function is going to infinity for any value of lambda, it turns out there is a narrow cave in lambda, L, and beta such that nothing blows up. Anything below or above this narrow cave will not work in our setting. And it turns out the lambda should equal to this function to be actually effective. So let me conclude. We provided concentration inequalities, which include all random variables with finite second moment. They are ready to use inequalities. There is no free parameter. And we precisely characterize the sub-Gaussian region and the other region whose behavior is characterized by the rate function. We have shown our results are asymptotically sharp. And finally, this inequality has many applications in machine learning and data science analysis. Thank you.